Okay. So let's get a screenshot of that. All right, so we are asked about surface area here, and surface area just uses the formulas we got in chapter 11. So since this right here is a right rectangular prism, then each face is a rectangle, so we just have to identify the different faces. So we've got this front face here and the corresponding back face that are going to match up. So we're going to have two of those, and those two are 8 by 11, according to the picture. I have 2 at 8 by 11. And then we just keep moving around, getting corresponding faces. So this is kind of like that activity 8 we did. We were supposed to look at each shape, figure out what it is, figure out its measurements. So this side over here, and it has a corresponding matching side on the other side. There's 2 of those, they're 12 by 11. And then the top and bottom faces, those are going to be what, 8 by 12. There's 2 of those. And read that. So I just need to make those calculations and then add them up. So we do that here. Let's see, 8 times 2 is 16, times 11 is something like 176, I hope. Times 12 is 24, times 11 is 264. 2 times 8, 16 times 12. This one's a little harder. It's 160, 32, 192. Anybody help me on that one? 2 times 8 times 16. So 2 times 8 times 12.
250, 190. Oh,
92. Okay. So that's all of the different surfaces. So we just add them up, and that's the surface area. So 12, 1, 3, I think, 632 centimeters squared, because each of these measurements is in centimeters.
I think
multiply them.
I think I may have counted wrong. Because on mine, the answer is 120, and I just said 220. So I wondered if
So you must have had like a multiplication error somewhere or an addition. Yeah. You did something like this?
Yeah.
Broke down each area. Yeah. So the next one, we just have to remember the area of a circle, and then to figure out what's going on around the edge of this thing. And what happens when you unwrap the label of a can? What do you get?
rectangle.
You get a rectangle, right? So we have 2 circles. We'll deal with those in a minute. And then we have the label, basically, is the outside of the can. And the length of this, let's do color, that way is this piece right there. So I had to cut it and wrap it. So how would I calculate that based on given information?
The circumference is 2.
Yeah, that's the circumference. Yeah, so that's just 2 pi r. So this side right here is the circumference of the circle, which is 2 pi r. R is 12. And then, we're given the height there. That's just our 8. So then this surface area here is just going to be that 2 pi r is 12 times 8. And we're going to have to plug that in the calculator, unless they wanted an exact answer. I forgot what I said. Oh, that's this one still. What did we come up to on that one? I forgot now. 632. Let's see what they're going to ask about the next one. Fantastic. Okay, so they want us to leave the pi as pi, not use the calculator pi or use 3.14. So this is part of the surface area right here we just calculated, whatever that ends up being. And then we have to factor in the top and the bottom. So what's the area of the top? It's going to be pi r squared. And so I'm going to have 2 for the top and bottom. Of those pi r squares. And in this case, r is 12. And then I'm going to have to add that onto this right here. So I'm going to bring that to a new screen so it's room to write more. So I've got the edge of the cylinder. That's 2 times pi times the radius. This radius was 12. Times the height. So that's the label part. And then I have to add on to that 2 times pi times radius squared. And then we're asked to clean that up and leave pi alone. So we just need to do some careful. It's kind of like a little bit of algebra. So let's see, what's 12 times 8 is 96. 96 times 2, that 192. Yep. Okay. So the first part gives me 192 times pi. It's wrong order. And then the second one, I've got 12 squared, which is 144. And if we double that, we get 288 pi. So how do I get to the final answer? Can I just add those two and pi just hangs on? Pi is just a number, yeah, so it's just tagging along. So I have 192 pi's and 288 pi's. So 192 plus 288 is 480, so I have 480 pi, and that's centimeters squared, because we started with centimeters, should be the final surface area.
I was having problems with square roots.
Okay, so that would have been,
It was
let's see, that comes up in the surface area too. Yeah, so there should be problems with square roots in this section. All right, so 480 pi, and I think you can just type pi to get it. Excellent. All right, so, okay, so let's do it. Screenshots. Which one, the first one or the second one? All right, so we want to find, again, the surface area. So how many different pieces do we have to this surface area? Almost 3. Why 3, not 2?
Oh, because it's the top.
Yeah, there's the top half sphere, semisphere. There's the cylinder, and then there's the base. That's a circle. So we have to identify those 3 different things. So for my semisphere right here, all that really matters is its radius. So what's the radius of the semisphere? 5, yeah. And then does anybody recall from last time while reading the book what the surface area formula for a semisphere is? Similar to the area of a circle.
It'll be pi r squared.
Is it?
Is it pi r squared divided by 2?
Almost. It's pi r squared, but it's times 4.
Are we going to have to remember all of these formulas?
Nope.
Are we doing up and down test together like we did last time?
Sure. But there's a time limit. normal class time. Trust me, you'll finish it way less than that. I don't give long finals. So that's the semisphere, right? So we plug in our numbers. We're going to get 4 times pi times that 5 squared. And I usually hold off the units while I'm doing the calculation and plug them in later. So 25 times 4. So the top gives me 100 pi. 25 times 4 is 100. So then, what's the side going to be?
It's going to be a rectangle again. So
It's going to be a rectangle, yeah. So calculate what the area of that label is. It's just like the one we did. So 2 parts to that. Your circumference gives me the length of that label for the cylinder. That's going to be 2 times pi times the radius of 5. And the height is 4, we just multiply by that. So the area of the label, the cylinder part, that should be just 45. Circumference times the height. And then last but not least, we have the base. So we have this circle in the bottom, and we know its radius. So then that's going to give us pi times the radius squared, which is 25 pi. 100 pi, 40 pi, 25 pi. So the total surface area of this thing should be 165 pi. And so it's not too much different than the 2D geometry stuff we played with. When we're trying to find complicated areas, we kind of break it up into different parts and find each part one at a time. And think about which formulas that we need. All right, what else should we do? We need to find one with square roots in it. I have one in mind if you don't see one in the homework, but we should see some square root stuff.
There was a lot in section 2.
In section 2, what was section 2 about? Oh, yeah, section 2 was the Pythagorean theorem. But we should be able to apply the Pythagorean theorem here. You had something too you wanted to go over?
I can't remember what's.
Okay, well, we can poke around there and take a look. Let's see, gallons of paint, that one's not too bad. Let's see what 7 looks like. Taylor, did you have some specific ones you wanted to look at?
Whatever one that you go over.
Whatever one would be good, okay.
All
All right, we got a soup can, or the paper label. That's a good review of what we just did. All right, blow this sucker up. All right, so we have a soup can that has a 3 5/8 inch diameter. As much as I love fractions, fractions of an inch are just such a pain in the butt. We really should use the metric system. So it's got a 3 5/8 inch diameter and it's 3 inches tall. What is the area of the paper that will be used to make the label of the can if the paper covers the entire lateral surface area? Just trying to cover the surface area, no overlap. Just get it perfectly. So what's the first thing you should do here? No. Draw a picture. Yeah. Anytime it's geometry, if the picture isn't given, try to sketch it, and then throw the other stuff in. You already did that. Okay. Yeah. So quick picture, and then we start whipping out our formulas. But I recommend drawing a picture first. So let's copy that. I think I'm going to do that. And when I first draw a picture, I don't really worry about making it to scale, and later if I decide if I should redraw it. So let's see. This is supposed to have a diameter of 3 5/8 inches. And then the height, it was 3, is that right? Okay, so about almost as tall as that is wide, but just a slight bit less. So I think roughly that's what the can's going to look like. A tall tuna can like this. What other cans look like that? A lot of cans instead of beans. Definitely not a bean can. Anyway, so this is 3 inches high. And again, when we unwrap that for the label, the top of the label, that length is just the circumference. Circumference is just, one way to think about it is just pi times the diameter. You could call it 2 pi r, but then you have to find the radius. But we already have the diameter. Right? So that's why I would choose this formula here. Because the circumference then is just whatever 3 5/8 is times pi. And then the height is just 3. Anybody remember rules about working with fractions? What's a good idea and what's not? Back before.
Make it improper.
Yeah, make it improper. Mixed numbers are such a pain in the butt to calculate with. So 3 times 8 is 24 plus 5 is 29/8 times pi. And we just need to get the area here, we just need to multiply that length, the circumference, that 29 pi over 8 times 3. Fraction-wise, we can look at that as 3 over 1. Do 3 and 8 have any common factors? No, they don't, right? So that means this nothing reduces ahead of time. So the only thing we can do is multiply the numerators and multiply the denominators. 3 times 29 plus 87. Did I do that right?
Mm-hmm.
Okay. So it looks like the area is 87 pi over 8. Be one way to state it. Ooh, what are the units? Not inches.
Inches squared.
Inches squared, yeah, because if we just go back here and think about, all right, this was inches and this was inches, and we just multiplied those two together. So this must be square inches, or if you prefer, inches squared. Ooh. Let's see if we can get a fantastic out of the computer. 87 pi, oops, not in the box. Oh, this time it says round to 2 decimal places. Okay. So in my calculator, I type 87 pi over 8. Calculator says it's 34.16. Anybody else get about that?
Yeah, that's what I have.
And you get a slightly different answer. So here I'm using calculator pi, which is like maybe 10 to 15 digits of pi. 2 decimal places shouldn't matter. 3.14 might give me a slight different answer.
I think the question said use 3.14.
Oh, it did say, okay, so I'm not very good at reading the fine print. That's my wife. So here I get 34.15 if I use 3.14 instead of a calculator pi. Use 3.14159. Okay, so they got pretty specific there. Someday I will learn to use fine print. So now it's 34.16. Variety of answers depending on how you choose to round pi. That's okay. So 34.16.
So could we have just changed the fraction to a decimal to begin with?
Given that it said this here, yeah, so we could have just typed 3 5/8 in and used its decimal version and just kept going from there. Usually I keep pi till the end, and then in case I don't want to introduce any early rounding error on the computer system. All right, let's see. Usually they're more exciting at the end. Let's see number 13. Oh, yeah, this is one of those student wonders. Let's do it while we're here. A student wonders if she doubles each measurement of a cereal box, will she need twice as much cardboard to make the new box? How would you help her decide? So they give a bunch of explanations here. One of them is right, and the others are either almost right or very wrong. So just think about that for a minute. So draw a rough sketch of a cereal box.
What number is this?
This is number 13. Do your best artistic rendering of a cereal box. There's mine. So I've got this length here, and I've got this width here, and I've got some height here. You could even put numbers in there if you wanted to. And what we want to do is, again, double all of the dimensions. She wants to double each measurement on a cereal box. Well, she's going to double each of those. So I'm going to try and draw double that next to it. So double that length is going to be, so there's the length, and there's the length again. Double the height. I'm going to do about that big. And then double the width. I'll be about that wide. So there's my twice as big cereal box. So is she going to need twice as much cardboard to build the box? That's what she's wondering. So just kind of put it in perspective. The original box had half that length, half that height, and half the width. So here's the original box superimposed on there. How many of these faces do you see here in the front of this new giant box? There's actually 4 of them because I doubled. So I have 1, 2, 3, 4. So is the new amount of cardboard double, or is it something else?
Would there be 8 of those inside of it?
Well, so I'm just talking about surface area, not volume. Yeah, that's a whole nother question. Okay, so here, if we're just talking about surface area, if she doubles each dimension, you double the length and you double the width. If you just look at that face, you now have 4 times the area you had before. Now, Nikki's right. If you think about volume, which is a 3-dimensional measurement, then you also have another box sitting behind this one, right? So how many boxes would you end up with if you filled the new cereal box with old cereal boxes? You would get, say it again, you would get 8 of them. Yeah, and that's 2 times 2 times 2, because we doubled the length, doubled the width, and doubled the height. So surface area wise, oops, wrong way. I had a length times a width, and there were 2 of those. Okay, so let's see, length and width. What was that one? That would be the bottom and the top of the box, right? And then there's 2 that have the length and the height. And then there's 2 faces that have, what am I missing? Width and height. That's the size of the box. So this would be the surface area of the original box. What did we do to each length and width? We doubled them, yeah. So our new big box, big surface area, is going to have 2 faces that are twice the length and twice the width. It's going to have 2 faces that are twice the length and twice the height. And it's going to have 2 faces that are twice the width and twice the height. And altogether, what we did is we introduced a pair of 2's multiplied in each term there. We factor those out, then that's going to give us 4 times the original surface area. Which is that right there. That kind of makes sense from an algebraic point of view. I like the picture point of view better, but that's the algebra point of view of it. The volume is kind of easier to look at because volume is easier to calculate. Here for a box, oops, box volume is just length times width times height. For our new big box, we're going to have twice the length times twice the width times twice the height. And multiplication, you can multiply in any order you want. Okay? So we have the commutative and associative properties working together. So I can rewrite that as 2 times 2 times 2 times the length times the width times the height. And so there's that 8 that we were envisioning geometrically.
On your big surface area.
Yep.
How did you get 4? Like, I understand why, like, in the picture. Why
Yeah, so-
4, but
So she said she's going to double every measurement. So instead of just having a length, I'm now going to have twice the length. Instead of just the width, I'm going to have twice the width.
oh,
And so each time I introduced a 2 and another 2, 2 times 2 is the 4 that I'm factoring out. So every term gets an extra factor of 4 because we're doubling. And because it's area, we double the length and a width or width and a height. 2 times 2 each time is that 4. Yeah, so that's kind of the geometric way. And you guys have had algebra, you can handle the geometry, but kids can totally handle, the algebra. Kids can totally handle kind of playing with this. And pulling out blocks is a great way to do it too, because not all kids are good drawers. All right, so I'm not going to bother reading through those 4 examples. You guys can do that, but I think you're on the right track to answering that. All right, let's look at one more of these, and then we'll take a look at Pythagorean theorem type stuff. If none turn up here, what's 11 look like? Total surface area of a cube. What is the length of one side? What is the length of a diagonal? Okay, this will likely lead to the Pythagorean theorem and a square root, I think. So let's pick it apart, see what we get. Oh, there it is. What's the first thing we should do? Draw a picture. Yeah, seriously, draw a picture. It frees your mind to think a little about it. So I have a cube. So usually to draw a cube, I draw a square face and then do my best to make it look 3D. So there's my rough square face. And there's the rest of my cube. All right, so we're given a surface area. All right, so let's think about that for a minute. So since this is a cube, every length here, what I normally call the length, is actually the same as the width. So I'm just going to call them all L for length, for some length. So the length, the width, and the height are all the same. I'm doing surface area, so that means I need to find this region here. What's the area of that face right there, for example? Yeah, it's just L times L, or L squared. And because it's a cube, what can I say about all of the faces? They're all the same, yeah. So the surface area here, how many surfaces do we have? 6 of them, yeah. So it should just be 6 times L squared.
Is that 13,000?
That says, yeah, so they're also telling us that surface area is also 13,472 square centimeters.
then you could divide by 6.
So we'll divide by 6, yeah. So let's see. 6 goes into 13,472. 6 goes into 13 twice with 1 left over. 14 twice with 2 left over. 27 is what, 4 times? 3 left over. And 32 is 5 times with 2 left over. Did I do that correctly? Anybody with a calculator? 1,245 and 1/3. I reduce it, or 0.33333. And do they want exact or approximate answer? Round to the nearest integer, okay? So we don't have to worry too much about that. 2/6 is 1/3, so that should be approximately 2,245. Let's go 33 is probably enough decimal places. That's L squared. So what do we have to do to get rid of the square? Yeah, take the square root of that, and that will give us our approximation for L. Square roots are not fun by hand unless you're really bored. What do we get for square root of that? About
47.384.
27.3.
47.
47.3.
38.
Okay, so we'd call it 47 would be the nearest integer version. And what are the units of that? It was centimeters squared, but we took the square root of that square, so it's just in centimeters. So it's about, the length should be about 47 centimeters. To double check that, we could plug it into the formula here and see if we get something close to that 13,000. So if I take my 47, raise it to the second power, and multiply it by 6, I get 2,215. Oh, shit, did I add? That's a problem. Times, I get 13,254. Oops, where'd it go? Yeah. So the decimal places make kind of a difference, but I'm in the ballpark. All right, what is the length of a diagonal that is not a diagonal of a face? Ooh, that is a hard visualization one. So try to draw what they're saying. A diagonal that's not a diagonal of a face. We draw a cube. I'm going to use dotted lines to draw in the sides that I can't see. So there's my cube. So let's see. If I start at this vertex, I can't go to that one right there because that would give me a diagonal I can see on a face. That gives me one on a face there. If I go to there, that gives me a diagonal on a face. So I think the only place I can go from here is over to that opposite vertex over there, cutting through the whole thing. So let's see, how can we figure that out? Thoughts? What's that? Yeah, if I can work with triangles, I can figure it out. So here's one way to, there's two ways to think about it at least. One way is to say, well, is this diagonal dashed line I drew there part of some right triangle? Okay, so then I got to figure, well, which right triangle is it part of? Well, if I drew, let's say, this diagonal in the base there, then this right here makes a right triangle. Okay, that'd be one way to think about it. But then I would have to know this diagonal through the base there. What measurements do I have to work with here? Well, I have that that's the same length as that, which is the same length as that right there. So how am I going to find out this bottom blue line? Let's highlight it. How am I going to find that line right there?
Well, find the hypotenuse.
Yeah, it's the hypotenuse of this triangle right here, because that's a right angle right through there. Yeah. Okay, so help me do that. What are the legs of that triangle?
47.
If I go with that approximation, let's see, is it safe to go with that approximation? Let me see what they're asking again. Type this number in and see if they give any finer instructions. Round to the nearest integer as needed. I think if we go with 47, it might be a little too crude, but let's give it a shot. Because we're introducing extra rounding error because the 47 was rounded. So we think L is 47. So each of these is about 47 each. So that means this bottom triangle, Pythagorean theorem says it's 47 squared plus 47 squared, and that has to equal that lower diagonal. I'll just call it D squared. Anybody have a value for 47 squared?
2,209.
2,209?
Mhm.
And then we have two of those, right? So that's going to give us 4,418. Is that correct?
Yep.
So then the diagonal I want must be the square root of that. So now I've got this, now I know this line down here, highlight color. So I've got that right there. I know this side right there, so am I ready to find the final diagonal? Yeah, so to find that final one, I'll switch to black, I'm gonna come up top. One leg is 47. The other leg is the square root of this number right here, which is gonna come up messy on a calculator. So I'm just gonna leave it that way for now. So I have to square 47, and then I have to take that number, square root of 4,418, I have to square it, and that's going to be equal to the, I'm going to call it big D squared. So that length squared plus that length squared right there. What happens when you square a square root? Gets rid of it. Yeah. So that means I have 47 squared. That's 47 squared, that is what, the 2,209? And I have this 4,418 to add to it. Altogether, that gives me 8,827. Did I do that right?
6,627.
Oh, 6,000. What did I get? 6,000. So at least I got the 27. And that's equal to my big D squared, right? So finally I can take the square root of that, and that should be about what I'm looking for, whatever the square root of 6,627 is. Now keep in mind, because 47 is rounded and we use it over and over again, we're introducing rounding error to the answer. So the computer might not be happy, but what is this to the nearest whole number?
81.
81? That seems reasonable. This is about 50, that's about 50, that's 80-ish. Yeah, seems reasonable. It's not too far out of line. So let's see if the computer likes it. And we're going to actually, no, let's check it a different way. So I just want to point out something about what happened over here. Where'd that 4,418 come from?
It was the two sides of the right triangle.
Those guys right there, right? And we had to square that square root, so it got rid of it. Well, the 4,418, that is this sum right there. So I can replace 4,418 with 47 squared plus 47 squared. And that's kind of interesting if you think about it. So I'm going to redraw my picture. Something like that. And we're saying that's 47, that's 47, and this is 47. And we ended up with a 47 squared, which was that side right there. And then these two 47s gave us this lower diagonal. So we had to add on that 4,418, which came from 47 squared plus 47 squared. Each of those 47s represents another way to get from this point to that point. Either I can take the shortcut along the diagonal, or I can travel 47 this way, 47 that way, and 47 that way. And that's each of those distances right there. So the cool thing about this is a three-dimensional Pythagorean theorem. So we have this, basically what we built here with this, and that right there, is we've built ourselves a triangular pyramid. And to find the longest length of the triangular pyramid by tracing these steps right here, say, we get a Pythagorean theorem with a 3D like to it, which is kind of wild. So there's the 2D Pythagorean theorem that we're familiar with. It turns out there's a 3-dimensional version of it too, which is kind of wild.
Does that really work?
No, it's a general property of 3D objects. Yeah, so we can use the Pythagorean theorem to find the distance across a right triangle, but it turns out this 3D Pythagorean theorem allows you to find the distance of any 2 points in space. Yeah, so like think about this room here. If we wanted to get make a wire from one corner to the opposite corner of the room, it's the 3D Pythagorean theorem that tells us how long that wire has to be. Yeah, so this works for any points in space. So it turns into a 3-dimensional distance pointer. It's kind of cool. All right, that's way more information than you wanted, but it's wicked cool geometry. All right, let's go take a look at, oh, I want to see if the homework system's going to like our rounding error. We ended up with 81. I'm thinking it's going to say, no, it's too much rounding. Oh, it liked it. Okay, cool. It must have left us wiggle room for rounding. All right, let's go and try a different one in another section. How do I get out of here? I hit save. And then I can go OK. And 11.2, 14.2, right? Almost done. All right, a particular one, or should we just browse? Okay, let's start with 7 then. Bar. Oh, that's a cute one. Let's try it. We want to find X and Y here. Page. So this is like a Staggering Puzzle. Oops. Oh. So this is number 7 in the homework for 14.2. All right, so we need to find X and we need to find Y. And we have how many right triangles here? Almost 3. Yeah, if that's a right angle right there and this is a straight line, then this has to be a right angle too right there. So turns out we have 3 right triangles to play with here to try and puzzle this out. So what jumps out at me right away is if I know these 2 sides right there, and that's a right angle, Pythagorean theorem says I can find that longer side over there. So according to Pythagorean theorem, I should be able to take that 8 square root of 3 and square it, add that to the other leg squared, and that should be equal to the long side squared. So squaring something just means multiplying it by itself, right? And Tiffany, I'll record the next part for you too.
Thank you.
Yeah. So I have 8 square roots of 3 times 8 square roots of 3. What happens when I take a square root times itself? It squares it or cancels the root. So this is going to give me 8 times 8, which is 64, times 3, whatever that's going to be, plus another 64 over there. So help me out with the calculator here. Altogether, I think that gives us around 128. 256. Thank you. 256 is x squared, and to get the x alone, we can take the square root. And I think 256 is a perfect square. 16 maybe? Mm-hmm. Cool. That's exactly 16. All All right, so let's see. Next, we need to figure out y, the altitude. I see at least two ways to do that off the top of my head. Anybody want another piece of pizza, by the way?
I feel like when I asked for help, it said something about a 90, 30.
A 30, 60, 90 triangle?
Yeah. I'm like using the equation for that.
I had a really hard time with the 30, 60, 90 thing. I didn't understand the instructions I was trying to read.
Yeah, did you read about the 30, 60, 90 earlier in the book and that didn't help? Yeah. I don't think it's obvious that that's a 30, 60, 90 triangle. But we can compare it to one in a minute and see. Yeah, so that's not the route I would take. The harder, yeah, I think that's a harder way to do it. But the problem is you never know which is the harder or easier way, so you try a whole bunch of different ways. So, okay, so if their claim that it's a 30, 60, 90 triangle is correct, we'll test that in a minute. That's one way. Another way I was thinking of is that this, if I consider that 16 to be the base, then this would be an altitude or a height for the triangle from that way. So I can relate this to the area formula for a triangle and try and solve it that way. The other way to do it is to kind of break this side up using another variable, but that'll give you a system of equations. We don't want to do that. Yeah, so here's the observation I'm going to make. I know that this side 8 and 8 square root of 3, that those two sides are perpendicular to each other. So the area of this triangle, according to those two measurements right there, is 1/2. I'm going to say 8 is the base times 8 times that would be the height then, 8 square root of 3. And I can clean that up a little bit. So let's see, if I clean that up, the claim then is 1/2 of 8 is 4, 4 times 8 is 32. Without a calculator, the best I can do is say it's about 32 square root of 3 for the area. The other way to look at the area, which is black, is to say this is the base and y is the height. So the area is also equal to 1/2 of the base of 16 that we just found times y, the height. And so if we just relate these two, we can solve for y, because they have to measure the area in the same way. So I'm just taking two versions of the area based on having two different bases and heights I can use. So taking that to a new screen, 1/2 of 16 is 8. So I can say area-wise, 8 times y has to be the same as 32 times the square root of 3. How can we solve for y? And just divide by the 8. So 8 goes into 32 4 times, so y should be 4 times the square root of 3. Now I should see if that's a reasonable measurement here. So calculator, can somebody help me out? What's 4 times the square root of 3?
6.928.
Okay, so let's call it about 6.9. And then didn't we have an 8 square root of 3 there also? Yeah, so 8 times the square root of b would be twice that, so that's almost 14, 13 point something, 13.8-ish. So do these make sense? So x is about 16, right? Exactly 16. And it came from a triangle that was almost 14 by 8 in that direction. If I just focus on, let's say, this little triangle over here, if the long side of that little triangle is 8, does it make sense the next longest side's about 7? Seems reasonable, especially if this picture is drawn to scale. I'm not clear it is, but it might be. Okay, let's take a look at their 30, 60, 90 triangle claim. So there must have been an example in the book that was similar to this that led them to use that. So 30, 60, 90 triangle. And there's a couple of different versions of looking at this. So I have a right angle, and then one of my angles has to be 30 degrees and the other has to be 60. So I'm going to claim that right there is my 60-degree angle, and this one's my 30 degrees, to the best of my artistic ability. The trick to figuring out a 30, 60, 90 triangle is to make a mirror image along the medium side of the triangle, like that. That gives me another 30-degree angle right here, and another 60-degree angle right there. So what is the mirror image created? When you look at it as a whole. A regular triangle, which is also called equilateral. Yeah. Okay. So what's the best way to do it? I'm going to say the diagonal. I'll say the diagonal was 1 unit long. So this side right here has to be 1 unit long because that's the same diagonal. And what can you tell me about this bottom length right here?
It's the same length as
it's got to be 1 also. Okay. So if that's a 1, then what does this original small side have to be? It's got to be 1/2. Now, what I don't know yet is I don't know the altitude for this original medium length of that triangle right there. So we're going to call, I'm just going to call that A for now for altitude, or A, one of the legs. So Pythagorean theorem says that A squared plus 1/2 squared is equal to that long side 1 squared. 1 squared, sorry. Cleaning that up, that gives me A squared plus 1/4 equals 1. Now I'm trying to get that altitude here. So I'm going to subtract the 1/4 to the other side. So 1 minus 1/4 is going to give me what? 3/4. And then I have to take the square root of that. So the square root and the square pretty much cancels. In some circumstances, you get a plus or a minus, but since this is a length, we only want the positive version. Cool thing about the square root of a fraction, if everything's positive in there, that's the same as the square root of 3 over the square root of 4. Square roots break up on division. And why is that cool, writing it that way?
You could reduce it.
Yes, square root of 4 is 2, so I can say, oh, this is the, whatever the square root of 3 is, just cut that in half after. All right, so the algebra is not as important. The symmetry is pretty important, that how we can figure out all the side lengths of a 30, 60, 90 triangle, because it's half of a regular triangle or equilateral triangle. But now I have measurements, one form of measurements for each side. So the measurements we just came up with is that if this is a 30, 60, 90 triangle, and the hypotenuse is 1, the short side has to be half of that, and the medium side has to be square root of 3. You could look at it as square root of 3 times 1/2. So it's square root of 3 times that smaller side. Now, all 30, 60, 90 triangles, no matter how big or how small, are the same shape. So their claim was that their triangle, I'm just going to reorient it, let's see, is bigger than this one because they said the long side was 16, the short side was 8, and the medium side was 8 square roots of 3, is what they claimed. So if two figures are similar, same shape, then their side lengths must be proportional, like one's blown up from the other or shrunk down. Does anybody see a proportionality factor to get from the blue triangle to the red one? How many, so it's not to scale exactly, but how many times bigger can you tell me is the red triangle going to be?
16 times bigger.
Yeah, so let's check that. So guess is that it's 16 times bigger because if it's the same shape. So that's, you know, from this observation right here, what's 16 times a half?
8.
8. And if we take the square root of 3 over 2 times 16, 2 goes into 16 8 times, and that does give us that number. So the only way to know a triangle is 30, 60, 90, there's two ways. One, you measure each angle, which wasn't easy to do in that particular problem, or to show that the side lengths are proportional to some other 30, 60, 90 triangle. Once I know that, then I can figure out any side I want, once I have that idea. All right, so that's part of what I think they might have been getting at, and it helped me solve this. Here's the other part. So here's the original version of the triangle they gave us. That's supposed to be a right angle right there. Let's make believe it is. This was 8 square root of 3 here. This was an 8 there. We easily found that to be 16. That's what they call x. And then they threw in another side right here, and they called that like y right there. All right, so let's see. Can you tell me anything about this angle there or that angle there based on the previous screen? So we've just shown this is a 30, 60, 90 triangle because the side lengths are proportional to another 30, 60, 90. So which one of those angles is 30 and which one is 60?
On that side would be 30, I guess.
Yeah, because 8 square root of 3 is bigger than 8. So the angle opposite the smallest side has to be the smallest angle. So that's got to be 30 degrees. And the angle opposite the medium length side has to be the medium length angle. Now, angles and sides aren't proportional in a right triangle. However, the idea of smallest angle has to be opposite the smallest side, that does work. All right, cool. Now check this out though. This is a right triangle over here on the left, isn't it? One of its angles is 60. What's the other angle have to be up here in the corner? Got to be 30. Yeah, so it turns out when you draw an altitude through the long side of a 30, 60, 90 triangle, you cut it into another 30, 60, 90 triangle. Not only that, this triangle on this side is also a 30, 60, 90 triangle too. So there's two 30, 60, 90 triangles living inside the big 30, 60, 90 because of the altitude. Which, I don't know, when I first saw that, that blew my mind. 3 30, 60, 90 triangles live inside each other perfectly. Yeah, so their point and the hint is now that we know this little triangle is a 30, 60, 90, we could use proportions to find that missing side right there, instead of the Staggering theorem that we used for the area formula. Should we continue that? Yeah, you look like a deal there. So what we figured is that this red triangle is the same shape as the big one, which is the same shape as the one I played around with a minute ago. So what I'm going to do is I'm going to take my original big triangle here. I'm just going to reorient it like that one. So this side right here is my 8. This is my 8 square root of 3, and this is my 16. So I'm just taking that big black triangle and just redrawing it this side there. I want to compare that with this new triangle. And I'm kind of trying to, sorry, I'm having a hard time drawing to scale today. These are supposed to be the same shape. You squint, it might work. So I know this side right here is 8. I would like to know what that side y is right there. So I could make a proportion by doing something like, let's switch to black. I want to know what y is. And I know the long side 8. So what I have is basically the medium length side in the top and the long side in the bottom of my fraction for this triangle. So now I have to make a similar fraction from this triangle. So what should my numerator be? What is the 8 related to in the big triangle? To the 16. Oops, down here, 16, sorry. And what is the y related to? 8 square root of 3. Yeah, so I can solve this by proportion. So what do I do to get y alone here? Yeah, I can just multiply by 8. Yeah, you can cross multiply and divide, but I could simply multiply the 8 up to the other side. So then I just have to think about, okay, how do I clean up 8 times 8 square root of 3 over 16? So 8 goes into 16 twice, and then this 2 goes into 8 4 times. So we get the final answer would be 4 times the square root of 3 once I clean it up.
Could you, because it's 30, 60, 90, could you have the bottom side, the short length is going to be half of that? Could you just take?
So that this is going to be a 4 down here?
Y would be 4 square.
And this is always going to be square root of 3 times the short side. Yeah, so that'd be another way to do it too, which is using proportions in a different way. Yeah. So like I mentioned in the beginning, there's a ton of different ways to do it. You never know which is the easiest until you try a couple. I can't answer that. Sorry. This is pretty complicated. I tend to put really complicated problems on a take-home test and do simpler questions in the in-class part. That I can't tell you.
I was having a really hard time with number 6.
In the same section?
Yeah.
Okay.
14-2.
All right, let me just zoom out.
That one took me like 10
That was the one where it wasn't accepting my answer.
Yeah,
Okay.
that's the one I was thinking.
All right, so find the area of the rhombuses given to the right. Okay. So, do I have on the screen somewhere? Oh, you go way back here. There. Screen. Screenshots. All right, let me just take them one at a time. Ooh. All right, and we want area, is that right? Find the area, okay. So I'm assuming that by that 4 right there, that they mean just that part right there. You guys agree with that? Okay. So I know that's 4. I know that's 17 right there. Let's see. In order to find area, I need a base that is perpendicular to a height. So what comes to mind on this one right here is if I do just some dissections of this, so I can break this into 4 congruent triangles, and then I can reassemble them. Oh, that's this. So what I'm doing is I'm taking these bottom 2 and I'm rotating them up into the upper part here. And if I do that, what do I get? I get that these diagonals are my 17s here and here. And I get that this is 4 there and this is 4 there. So my total distance across is 8. All I need to do is figure out what is that height right there. And then I'll have base times height for the area. That's one way to look at it. Can we figure out that height? Do we have enough information?
Yes.
And we have our right triangle that's 4 by a base of 4 and a diagonal of 17. So I'm going to call that an altitude. I'm going to call it A. So this leg squared, A squared, plus this leg, 4 squared, has to equal 17 squared. That'll give me the altitude that I need. Let's see, do I know 17 squared? No. The something 9. $189? 17 squared? So I've got 289 there, I've got 16 here, and the A squared is hanging out. So I'll have to subtract that 16. So A squared is 273. So A is the square root of that. 273 is not a perfect square that I recall. That's probably going to be a messy number. They want an exact answer or a rounded answer? They want an exact answer using radicals, and we need to simplify the answer. Okay. So I'm assuming.
That's where I was getting confused. I don't know how to simplify.
Yeah, so to simplify this right here, we just do a factor tree on it. So what divides into 273? So let's see, 2 doesn't, but I think 3 does. How many times does 3 go to 273? What is it?
91.
91, okay. So 3 times 91. What goes into 91? 13?
Yeah.
Okay, what is it?
Is that 13 times 7?
13 times 7. And so that, since there's no repeated factors in there, 273 doesn't simplify. But what I know is that's the height of my figure here, and I know the base. So the area has to be 8 times the square root of 273. And since there's no repeated factors inside 273, it doesn't reduce any more than that one. So that should be the final answer. So we'll try the next one, see if it's any more challenging. Yeah, so the other one's going to have different numbers, so we'll see how much different that is. 8 square root, like that. Use their buttons here. 273, is that what we had? Fantastic. All right, let's try the next one. So, you want to have a different set of numbers you want to try?
Just, can you find the area of one of the triangles?
Mm-hmm, that'll work too, yeah. All right. So let's do it that way since you mentioned that. So I have a triangle here that I can isolate. And I have a base, I just need to know what the height there is. So I'll call that h. So h squared plus 2 squared is equal to 17 squared. And as we just saw, 17 squared is 289, is that right? 2 squared is 4. Subtracting 4.
Is it 2 all the way across, or just?
I thought they just meant that part was 2, is what I thought. And I assumed that in the first one, and I got the right answer. Yeah, I thought that was unclear from the picture. They could have made that a little more clear. So subtracting 4, I get h squared is 285. So h is the square root of 285. Now, since they asked us to reduce it, yeah, let's try to reduce that before we move on to the triangle part, making that 4 times. Well, 5 goes into it, right? How many times does 5 go into 285?
57.
7 times. And 57, 3 goes into that, doesn't it? 19. So the square root doesn't simplify, because 19 doesn't factor any further. Each factor is different. So we can't write that square root any simpler than what it is.
So
All
say
right.
you did have like a square root that had like 2 2.
Yeah, so let's I can just give you a different example. So suppose we had something like square root of 24. I was trying to think of a bigger number. 24 is 2 times 12. 12 is 2 times 6, and 6 is 2 times 3. So anytime you find a pair of numbers, you basically have a square root. The square root of 2 times 2 is just 2. So that comes out as a single 2, but those guys are trapped inside still. So the square root of 24 must be the same as twice the square root of 6. To double check you did that right, just type this in your calculator, get the decimal, type that in, get the decimal, and hope they match. That means you pulled out squares properly. So just a factor.
So if you had multiple, so if you had like 2 2s and 2 3s,
you'd pull a 2 out and you'd pull a 3 out. Yeah. So if we had, whatever 2 times 2 times 3 times 3 times 5, suppose our number factored that way. These 2 come out as a single 2. These 2 come out as a single 3, but the 5 is trapped inside. So it would be 6 square root of 5 would be the reduced version there. All right, so back to this one here. We now know the height of the triangle. One triangle area would be 1/2 the base, 2 times the height, square root of 285. That simplifies down to just square root of 285. That's just this triangle right here. So like you said, if we multiply that by 4, that should be the area of this rhombus. Sorry, 4 times the square root of 285 should be the area there. That help? A little bit? Taylor?
Yeah.
Yeah. All right, so I am going to stop this video here and go over some questions from the practice test. Stop button. Over here.